Hi everyone, we're the team behind Cloak, a man-in-the-middle packet capture and analysis system developed as part of UCF's Computer Science Senior Design course. My name is AJ Futo. I was the project manager for this project, and I also worked on networking and data analytics. I chose this project because I have passions for networking and cybersecurity, and I thought this would be a great opportunity to apply my interests and maybe learn something new along the way.
Hello, my name is Santiago Acevedo. I'm the lead front-end developer for Cloak, and I chose this project as an interest to branch into cybersecurity.
I'm Michael Bernhardt. I'm a front-end developer and I worked on the database. And I really wanted to apply the knowledge that I was learning in my cybersecurity classes at UCF.
My name is Dakota Daly. I worked on data analytics and data visualization. I really enjoy cybersecurity, so I've enjoyed working on cybersecurity in this project.
I'm Matthew Singh. I worked on data analytics and infrastructure. And I chose this project because I believe it have a real world impact on cybersecurity.
The problem our sponsor wants us to solve is there's no easy all-in-one solution to get a comprehensive look at all the network data going to and from a specific device with great accuracy. So we're developing a commercial system that solves this problem, which includes a capture device that we call the Cloak Device that sniffs the information from an end user's computer and sends it to a backend, which we call the Cloak Server, that ingests this captured information and displays it on a front end for an administrator.
So where Cloak can be used, mainly it can be used for IT departments, where IT administrators can monitor employee traffic for malicious or unproductive activity. Privacy research, in terms of researchers can collect network traffic for their studies and papers, and all in all, in national security, allowing for government agencies to have an extra layer of monitoring network traffic to help their cybersecurity. So our goals that were given to us in the beginning of this project were to have a hardware component that is low profile and allows for collection of traffic, network traffic from the end user's device without them knowing. A containerized backend that designed to run on any cloud that runs CAS or a local server infrastructure, and a sleek dashboard that interprets and displays data in an efficient and easy way for the user.
So based on our project goals and objectives, we came up with 3 different project components. The first one is our Cloak device. This is our actual hardware. It's a single board computer. Right now we're using an Orange Pi, and it's what's actually deployed between the end user's computer and the network. It's what sends the data to our backend or to our database. We have our Cloak backend. This is what holds our database and all of our APIs. It's fully containerized. And then we also have our Cloak frontend. This is our dashboard for an administrator, so they can get a good look at all of the packet traffic.
We can see all these components working together in this diagram. At a high level, there are 2 people in this diagram. The end user towards the top left, who's someone like a corporate employee, and the administrator towards the bottom, who's someone like a sysadmin or other IT professional. The Cloak device is deployed between the end user's computer and the corporate network infrastructure. Any normal network traffic going between the end user's computer and the internet, following the line in green, must go through the Cloak device. The Cloak device then captures it and sends it to the server following the red line. The backend ingests it, puts it in the database, and allows the administrator to access the information on the front end via the data analytics API.
Looking at the device now, the computer is plugged into the Cloak device and is connected to the network through the 2 Ethernet ports on the device. These 2 network interfaces are linked by a network bridge, meaning any traffic following this green line must pass through the network bridge on the device. And when the traffic crosses over the bridge, our packet capture script is able to sniff the information and package it and send it to our ingest server, shown by the red line.
And these are the different components that Cloak utilizes in containers as microservices. The data ingest API consumes packets sent by the Cloak device and forwards them to the database. The database, in turn, which is a MariaDB relational database, stores the packet data efficiently, and an entire separate database is used to handle user information for authentication. The data analytics API provides packet information for the front end to display based on queries with certain parameters provided by filters, such as date ranges or protocols. The API utilizes the packet analysis engine to quickly retrieve this information from the database. And lastly, the authentication API authorizes and authenticates users on login by generating a JSON web token, which is just a temporary string to identify them.
So for data visualization on our administrator dashboard, we have a donut graph that shows network protocol usage. So it'll tell you the number of packets of each particular protocol type that was observed for the given time window. We also have a line graph that will just tell you the number of packets over that time window. And then we also have a choropleth that will give you more information on the source and destination information for the packets over that time window.
At this point, we'll be transitioning into a brief demonstration of our project. During this demonstration, we'll be following a story to describe a typical use case for Cloak. In this story, I'm a sysadmin that's responsible for overseeing a large portion of a tech company's network infrastructure, and we've just been a victim of corporate espionage. Some documents containing industry secrets have recently been found on a dark web marketplace for sale. Our legal team has identified these stolen documents and worked with middle-level managers to identify that it came from a team that falls under my domain. The middle-level manager has identified the work in question and that it belongs to our employee Matthew. This is strange because Matt's a commendable employee and was extremely proud of the work he did in this document, so it's unlikely that it's him. In fact, we can almost be certain that it's not Matt since he's been out of the office for the past 2 weeks. He took a well-needed work feed cruise to celebrate the success of completing this project. Matt's work laptop was left in the office, locked in a cabinet, and he has no access to the corporate network from any of his personal devices, so we're pretty sure Matt's out of the question. Our information security team looked more closely into the firewall logs, and they were able to confirm that it wasn't Matt. They identified a vulnerability in a firewall that allowed a foreign actor to have access to Matt's PC and use it as a foothold in our network. I've been tasked by management, legal, and the information security team to find out what other damage, if any, this foreign actor did within our domain. Luckily, we did have a Cloak device deployed on Matt's computer, so we are able to look at the dashboard to see what information was collected. The first thing we notice is the spike of network traffic on April the 10th. This is strange because Matt, again, was out of the office during this time and had no access to his computer or the work devices. So this tells me that someone else must have been using Matt's computer to do something on our network. We can look at the network protocols tab to see what that may have been. We see a lot of TCP traffic, ICMP traffic, SSH traffic, and some others. These are all very commonly used protocols on the internet, but an attacker could exploit them to try to do something malicious. As we scroll down to the packets table down here, we are able to begin to identify some anomalous activity. As sysadmin, I do know that Matt's computer does have this .36 IP address, and it looks like the attacker is trying to use this computer to talk to other devices on the network, namely the .118 device, the .119 device, the .120 device, and finally the .121 device. The sequential nature of this is indicative of a network scan, so the attacker is trying to scan the network for any other devices that may be online and susceptible to some kind of compromise. It looks like the attacker has latched onto this .121 device and they're trying to establish some kind of communication with it. It looks like they're scanning this device over port 80, which is HTTP, port 8080, which is HTTP also, port 22, which is SSH, and port 23, which is Telnet. The attacker is likely trying to see if there's any vulnerable services that are running on those common ports that they can exploit. We are able to see that this device, the .121 device, is responding to the attacker's requests. On port 22, we are able to see that they do respond, so that lets the attacker know that this .121 computer is running SSH, which may or may not be vulnerable. The attacker then tries to establish an SSH session with this 121 computer, as we can see here. It's a little bit difficult to completely understand what's going on based on this, but we are able to download this as a PCAP file, which is an industry standard that allows network administrators and IT professionals to dissect network information. As we look at these SSH packets, we are able to see that none of them have a body associated with them, which essentially means that the attacker was not able to establish any kind of formal communication with the device in question. So the attacker is probably just trying a combination of common passwords and usernames to try to establish some kind of communication. After we scroll past the SSH, which again resulted in nothing, we are able to see that the attacker did begin to establish some kind of communication with a computer located in Russia, and the next several hundred packets are associated with that as well. So we see numerous packets going both to Russia and from Russia. We can generate a heat map based on this information to see more clearly where this information is going to and coming from. And as we can see, there's a whole lot of packets coming from Russia and a whole lot of packets going to Russia. So that's a lot of communication to a foreign country. We're able to then generate a report based on this information over the past week, filter it based on only Matt's device, and then generate this report, open it as a PDF, and send this to the legal teams, the information security teams, and the managers to let them know the result of this investigation. Ultimately, it looks like the attacker was only able to extract those files and send them to the Russian file server. They weren't able to do anything else on the network based on the data that we've seen today.